Now, the gap has gradually narrowed over the intervening period of time, but determinate remains are still quite rare prior to the late Visaean, and we're still in a position of not really having anything at all for the first 10 million years of the Tournaisian. So although it's not as large as it used to be, Romer's Gap, as it came to be called, is very much still with us. There's been a lot of discussion as to what this gap actually means, and broadly speaking, explanations have fallen into two categories. Either Romer's Gap is seen as an artifact of taphonomic bias or collection failure, so the tetrapods were there, but for whatever reason we just haven't been finding the fossils. Or alternatively, the gap is real, that is to say, there really weren't many tetrapods around. And that would suggest that there was some physical cause, that something about the environment perhaps meant that the terrestrial realm wasn't hospitable for these animals at this time. In 2006, Peter Ward and colleagues published what was to become quite an influential and much cited paper in which they offered a possible solution to this question. They proposed that Romer's Gap might be explained if atmospheric oxygen levels had fallen during this period. Excuse me. So that oxygen had fallen below some critical threshold beyond which these early limbed vertebrates were unable to cope. Their two main points of reasoning for this were, firstly, that the arthropods seemed to show a similar, although perhaps not a severe, diversity crisis at approximately this time. But more importantly, that what they were suggesting about oxygen levels matched the predictions of this paleoatmosphere model of Rob Berner. This is the geocarb-self model, and this was published in 2006. And Rob Berner was one of the co-authors on the paper. The thing about models, atmosphere models, is that there's quite a lot of them. They are quite complex. They tend to be based on a large number of assumptions that in practice are quite difficult to test. And as you can see, there's not really a lot of agreement between them. We don't currently have much of a consensus on quite what the atmosphere was doing during Romer's Gap. And what that means is it's very difficult to test ideas like that of Ward. So what we need is a more direct proxy for paleooxygen levels. And one possibility, which is what we've been exploring, is charcoal. So this is the product of incomplete combustion. And because it's quite chemically inert, it's actually quite common in the fossil record. It tends to survive rather well. So this specimen here is about 12,000 years old. The piece up there is from the Devonian. It's about 380 million years old. Large pieces like this aren't that common, but if you look at a microscopic scale, then we don't really find many sedimentary rocks that don't contain at least some charcoal. And charcoal in the fossil record is, of course, the product of naturally occurring wildfires. And clearly the availability of oxygen is going to affect the behaviour of a fire. You're always going to get some localised charring at the site of a lightning strike, for example, but if the oxygen supply is not sufficient, then you're not going to get self-sustaining combustion, you're not actually going to get a fire. And thanks to some quite detailed experimental studies that have been done, we're quite confident that we know the absolute lower limit of atmospheric oxygen at which you can get even very dry plant material to burn is around about 16%. So as soon as we find charcoal in the fossil record, that's immediately setting a lower limit on how much oxygen there could possibly have been in the atmosphere at that time. But furthermore, we also know that as oxygen supply is increased, the spread rate, the ease of ignition, the temperature of these fires will increase as well. So we should see a correlation between wildfire activity through geological time and atmospheric oxygen. So what we are trying to do is examine charcoal abundance in sedimentary rocks through the period of geological time that we're interested in, i.e. Romer's Gap, compare that to the charcoal content of modern sediments, which gives us a correlation point for modern 20.9% oxygen, and try and use that to test this idea. Now, this idea of using charcoal for this purpose has been explored before. This is from a study, and particularly by Andrew Scott and Ian Glasspool. This is from a study they did in 2010. This was based on the charcoal content of coals. And what they found, this is his, this Romer's gap here, what they found was there seemed to be a lot more charcoal than is seen in the most recent coals that they looked at, and also in modern peats. And they felt that that indicated oxygen levels that were actually quite substantially higher than today rather than lower. But the issue that you can see there is if you're relying on coals, once you get back to the early Carboniferous and certainly into the Devonian, there aren't actually that many coals around. So the sampling density is relatively low. So what we're doing to get around that is, rather than looking at coals, we are looking at dispersed organic matter extracted from other sedimentary rocks. And this is something we can do quite easily using standard palaeontological processing methods, so putting rocks through hydrofluoric, hydrochloric acid, making up these organic concentrates, and then examining those under using incident light microscopy to identify the charcoal that's in there. And charcoal at that scale can be distinguished quite easily because it has much higher reflectance than the other organic components. And this is something we can measure with some precision using our photospectrometer rig that we have there in the background. So if we look, so here's a sample, and so you see a number of these macerals, which are the organic equivalent of minerals, and here we have a piece of charcoal, which in this context we refer to as inertinite, which is clearly much brighter than this other piece here, which is vitrinite. If we make a large number of measurements and plot that data, what we see is the reflectance values show three fairly distinct populations, and that's telling us the relative abundances of the three primary maceral groups. So on the right, that's our inertinite, that's our charcoal. That's on the left is exonite, which is largely derived from spores, and just about everything else in the middle there is our vitrinite. So that gives us a quantitative indication of the relative abundance of charcoal, the relative abundance of plant material in here that has been burned. And the other thing that provides us with is also, it gives us a reflectance distribution for the inertinite itself. And the reason that's worth having is because there's a fairly straightforward linear correlation between the temperature of formation of charcoal and the reflectance. So if we were expecting to see some kind of change in fire behaviour, in fire intensity perhaps, then we would expect to see some kind of long-term trend, not just in the abundance of charcoal, but in the reflectance as well. Our sampling localities are the classic area in Greenland around Stensø-Bjerg, and this is the region where Acanthostega and Ichthyostega were found. So what that means is the area has been quite intensively studied, and we have quite a clear idea of the biostrata we're quite confident with. We know what time period we're looking at, we understand the environment. We don't need to worry about misinterpreting the geology that's going on there. The second area is the Bournemouth shore section. This is an area that's currently being studied as part of the ongoing TWEED project, the Tetrapod World Early Evolution and Diversification. So this is this collaborative, multidisciplinary attempt to understand everything that we can about what's going on through Romer's Gap. So this is something that my own work forms a part of. So if we excuse me. So during the time period in question, both of these localities were pretty close to the equator. I'm not sure how well it shows up, but that's the equator down there. So we're looking at coastal areas in equatorial conditions. So, and the benefit of looking at these areas that are probably just ever so slightly offshore or sort of marginal is that what you're getting is a catchment area. So sediments from the wider region are being deposited there, and rather than having to worry about the impact of local fire events as you might have to with coals, you're getting a good regional signal. So there's a balance to be struck here between the further out into the marine realm you go, the more regional it is, but of course the less plant material there is. So we feel that we've sort of picked a happy medium here. And this is just our actual coverage, so you can see that this is the area around Stensø-Bjerg, so we've got the uppermost Devonian and just crossing the DC boundary here, and then this is in Bournemouth, where we've got this interval that covers and just extends out the other side of Romer's Gap. And so this is how we're dating this with palaeonomorphs, so we've got our biozones established there, so we think we know what time period these things are coming from. So let's look at the results. On the left is inertinite abundance through time. The green bar here represents the abundance that we would expect under modern O2 conditions. So this is a value of 2.3% that we have established by looking at modern nearshore sediments. And our own mean value is actually very close to that. So it actually comes out at about 2.1%. So it seems that there's not very much difference between the two. And that's fairly consistent, not just through Romer's Gap, but before and immediately afterwards. So we're not seeing any obvious change as we pass into and out of Romer's Gap. There's a fair amount of short-term change, but when we're not seeing the kind of long-term trends that we might expect to be looking to see. On the right is our reflectance data, and with this it's very much the same thing. We're not really seeing any kind of long-term trend. We're certainly not seeing an increase or a dramatic increase or decrease in the temperature of these fires as we pass into and out of Romer's Gap. So what this seems to be telling us is that wildfire activity, as far as we can tell, was pretty similar to the present day. We're not getting a dramatic reduction. We're not seeing the much higher charcoal that Scott and Glasspool was seeing in their coal data. And the assumption here is that it's a small sample size, and it may well be that they've encountered some local fire event, something like that. But really what we're seeing is business as usual. We're not finding that we can support this idea of an oxygen low during Romer's Gap. So, in summary, as I say, fire frequency during Romer's Gap appears to have been very similar to the present day. We don't see any significant drop in fire activity at the start of Romer's Gap or at the DZ boundary. We don't see any notable increase afterwards, and we cannot support hypoxia currently as a cause of Romer's Gap. So, thank you very much, and if anyone has any questions.